So first, I want to thank the organizers for putting together this really nice conference and for giving me a chance to speak here. So what I'm going to be talking about is it's about long-range interactions and topological ground state degeneracy. And it's based on, I'd say, two different papers. One, which is a somewhat older paper that was posted about 1.5 years ago with Matt Lapa. And the other one is something we hope to post soon, is work with 21r-1a. So first, let me just sort of set up the question that I'm going to be interested in investigating. So, so the basic starting point is, as you know, as many of you know, there's many gapped many-body systems, or I should maybe say some gapped many-body systems have this very interesting property that when you look at their energy spectrum, you find a finite energy gap, and below the energy gap, you have some number of ground states. And these ground states are very nearly degenerate, with a splitting which is exponentially small in the system size. So they have an exponentially small ground state splitting. And what makes these systems interesting is not only do they have this nearly exact ground state degeneracy, but it's a robust phenomenon. There's no fine-tuning required. If you, in these systems, the ones I have in mind, you perturb the system under rather generic perturbations, you still see the same structure of exponentially small splitting and a finite energy gap. And this is, I think, interesting for many reasons, both as like possibly as application to quantum computation, but also just as an interesting phenomenon that occurs in many body systems, and it's connected to topological order and lots of other interesting phenomena. So, what are some examples of systems with this structure? So here I have a list of like 3 examples. The simplest is just systems with discrete symmetry breaking. Of course, you get some nearly exact ground state degeneracy with exponentially small splitting. Another example are one-dimensional topological superconductors, first pointed out by Alexei Kitaev. When you have open boundary conditions, you get this nearly exact degeneracy. And then, of course, there are basically topological phases, for example, in 2 dimensions. Maybe the most concrete example would be 2-dimensional fractional quantum Hall states. If you put them in a torus geometry, again, you get some nearly exact ground state degeneracy. Actually, it would be exact. You have translational symmetry, but if you break the translation symmetry, it becomes nearly exact. If you have magnetic translation symmetry, it's exact. So anyway, so here's some examples, and the question that I want to think about is, if you actually look at the arguments for why this phenomenon occurs, why you get this exponentially small splitting that's very robust. All those arguments, they require short-range interactions. So, say finite range or at most exponentially decaying interactions. And so what I want to understand is, what about systems with long-range interactions? And what I mean by long-range for this talk is basically power law interactions. So what happens in these systems? Does this phenomena still exist? Do you still have this exponentially small splitting? That's what I want to understand. Whoops. So why should we worry about long-range interactions? I think there are at least two reasons. One is there are actually many experimental systems, including some of the ones I listed there, where you do have long-range interactions. Probably the most prominent one is the fractional quantum Hall systems, which in many setups has an unscreened Coulomb interaction, power law interaction. And so it's relevant to many experimental systems to try to understand, will we really expect to see this this kind of exponentially small splitting in real systems with long-range interactions? I think it's also kind of a conceptual question, because it's a kind of question about how much, we know locality is important to the topological phenomenon, but how much locality do you really need? Is it enough to have just a few body interactions in your Hamiltonian, or is it important that they're local in space, and how local do they have to be in space for the basic, all the stuff that we're used to hold? Okay, so that's kind of maybe some of the motivation. And so what I'm going to do in this talk is I'm going to discuss a couple of concrete models where we can think about this question. And actually, most of the talk, I'm going to be thinking about this very simple one-dimensional model. So let me first let me tell you about this model. So the model I have in mind is basically just an Ising spin chain. So sigma z interaction, and then I'm going to add onto it some long range interaction, which will be like a sigma x interaction, where f here is some function that depends on the distance between j and k. And typically we're going to be thinking about the case where f is long range. And in the back of and again, when I say long range, think power law, like 1 over r to the alpha for some power alpha. And we want to understand what happens in this system. And this system, of course, a key feature of this system is that it has it's an example of a system with discrete symmetry breaking. So the symmetry in this case is Ising symmetry, product of sigma x on all sites. And if you turn lambda, if you turn off this lambda, you have a discrete symmetry breaking and an exact ground state degeneracy. So when lambda is 0, we get symmetry breaking and exact ground state degeneracy. But the question you want to ask is, suppose we turn on just an infinitesimal long-range interaction, what will happen? So there's two types of questions you can ask. The first question is, does the energy gap stay open? This model has an energy gap. It has, when lambda 0, it has an energy gap of order 1, and it has 2 exactly degenerate states. So when we turn on lambda, does the gap stay open is the first question. The second question, which is the main one that I'm interested in, is what happens to the splitting? Does the splitting remain, exponentially small in the system size, or does it have some other type of behavior? Right. This model I'm going to be talking about for a lot of the talk, and there's a couple there's several reasons that I'm interested in this model. One is it's just a very simple model which displays the phenomenon of a ground state degeneracy, where we can investigate what happens to long-range interactions. Another motivation you'll see later in the talk is it's kind of a warm-up for a two-dimensional model, which is of interest. But the third motivation is that this model on its own has some is connected to a physical system of interest, and that's what I have written here. So if you take this Ising spin chain model and you do a Jordan-Wigner transformation, so you map sigma x to the fermion number operator to ci 2 times this ci dagger ci minus 1, and similarly map sigma z onto this hopping and pairing interaction. If you follow through that mapping, what you find, as many of you probably know, is if you take that Ising spin chain, it maps onto this superconducting model. It has a mean field superconducting model where we have hopping terms, pairing terms, and then importantly, that long-range interaction, that sigma x interaction, after you do this mapping, it maps onto a density interaction. Okay, and so this altogether, this model is going to basically be equivalent to the famous Kataev model for a 1D topological superconductor with long-range density interactions. So even apart from the other motivations that I mentioned, it's just the simplicity and its connection to the 2D model, which I'll mention later. This is already kind of maybe a model of interest. You might want to know what happens to long-range interactions if you add long-range density interactions to the Kataev model. It's not a crazy system to think about. What will happen to the degeneracy? Yeah.
One famous long-range density interaction appears in the Schwinger model. Is that something related to what?
I actually am not familiar with that, so maybe
the gauge field in 1+1.
Yeah, I mean, I've heard of the Schwinger model, but I don't.
So your alpha would be -1 for that.
Yeah. So how would it correspond? Yeah, maybe we can talk afterwards how it corresponds.
Density interaction that goes like 1 over, I think, no.
Linear?
Oh, linear, right. Of course, it's linear.
It's linearly growing.
It's linearly growing. So
Yeah.
you're describing confinement, or
It
something?
describes confinement.
Yeah,
Okay.
the model is known to be gap completely.
And doesn't have any ground state degeneracy,
Right,
presumably.
right.
Okay.
But it has not been a representation. It's true.
Okay. So yeah, that's yeah. I think it's interesting maybe in its own right to think about this particular model. So first thing I want to do before I describe some results about this model is to try to sketch out for you why one might worry about what long-range interactions will do to this degeneracy, like why long-range interactions are different. So I'm going to describe this in the context of that specific model, this Ising model with long-range sigma X sigma interactions. So first, let's turn off those long-range interactions, and then you have two degenerate ground states. And it's useful to work in the work in the symmetry eigenstate basis. So the two degenerate ground states are the plus state and the minus state, which are these cat states, up, 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 plus, down, 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 and up, 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 minus, down, down, down. They belong to the two symmetry sectors, H plus and H minus, the two subspaces with S equals plus or minus 1. And they're exactly degenerate if you don't have the interactions. And now you might ask what happens when you turn on the interactions. And I'm going to sketch for you an argument that allows you to estimate how the splitting will scale. And so how does this argument work? It's in the case where the interactions are short range. So how does the argument work? So basically the idea is, okay, let's assume that the energy gap stays open when we turn on lambda. So then we'll get a picture like that, like this. You know, when lambda is 0, we have these two degenerate states and a gap. We turn on lambda, because I assume the gap stays open, you know, these states just stay below the gap, and then there'll be some splitting, okay? And I'll call the state, for finite lambda, I'll call the two states plus lambda and minus lambda. And we want to estimate the splitting between them. And so if the interactions are short range, there's a nice way to do this. And it uses something called quasi-adiabatic continuation. And I won't go into the details of how quasi-adiabatic continuation is defined, but the main point of quasi-adiabatic continuation is you can show if the gap stays open in a situation like this, there exists a unitary U lambda, which will relate your state at finite lambda to your state at 0 lambda. So there exists some U lambda that will do this, that will take plus to plus lambda and minus to minus lambda. And furthermore, in the case where these interactions are short range, you can show that this U lambda that comes from quasi-adiabatic continuation is locality preserving. So it has the property that, but what do I mean by locality preserving? If I take some local operator and I conjugate by U lambda, it only spreads the operator a little bit. Okay, so it's local in the sense that I said here super polynomially local. It means that this operator acts on one site. This conjugated operator may have a tails, but the tails decay faster than any polynomial. And so this, you can derive this from Lieb-Robinson bounds. The basic idea is this U lambda, it comes from something like adiabatic evolution. So it's like an exponential, it's a time evolution of a local Hamiltonian, basically. And so it has this locality preserving property. And this is what happens in the case where it's short range. And so now how can we use this to estimate the splitting? So to estimate the splitting, we want to understand that the difference in energy between the plus lambda state and the minus lambda state. So we just calculate the expectation value of H in the two states, take the difference. And then because, and then when you take this difference, you can easily see, because these are both these cat states, this difference is just the real part of this matrix element. And now we use the fact that U lambda is locality preserving to say that because U lambda is locality preserving and because H is a sum of local terms, this whole thing here is just a sum of local terms with, these very rapidly decaying tails. And any local term you write down will have 0 matrix element between these two states because, they differ everywhere in space. And so you can easily argue that this has to be super polynomially small. Okay, so this kind of argument allows one to show, and you can upgrade this argument to show it's actually exponentially small. So this kind of argument allows you to show that when you have short range interactions, the splitting has to be exponentially small, or in this case, super polynomially, or you can upgrade it to exponentially small. So that's how the argument works in the case where it's short range. But what happens if you tried to repeat this argument and it was long range? What would happen? The problem is that it basically comes down to the fact that you can still try to define this U lambda from quasi-adiabatic continuation. But now because we have long-range interactions in our Hamiltonian, this U lambda will not be super polynomially local. It'll be at most polynomially local. So we'll take operators and spread them with polynomial tails. And then if you try to repeat all these arguments, this has power law tails. And so the best you can ever hope from this kind of argument, and this is assuming you can do Lieb-Robinson bounds with long-range interactions, which only works for sufficiently rapidly decaying power laws. But even if all of that works, the best you could ever hope to get is a power law bound. And it really comes down to the fact that when you do time evolution with a Hamiltonian with power laws, it spreads operators much more rapidly than if you have time evolution with a Hamiltonian with local interactions. Okay, so this just shows you that we might expect long-range interactions to behave differently. At the very least, these kinds of bounds are much weaker. And so when we realized this, we started to wonder whether we would even expect exponentially splitting at all when we have power law interactions, because all the arguments that we could think of gave us at most power law bounds. And so the first result I want to tell you is that, despite the fact that those arguments don't work, the ones I just mentioned to you, despite the fact that quasi-adiabatic continuation doesn't give you a good bound, you can indeed show that you get exponentially small splitting if your power laws sufficiently rapidly decay. Okay, so for sufficiently high power laws. So that's the first result I want to explain. And so that's this stability theorem that was in our paper a while back. And so what does this theorem say? Basically, this theorem applies to particular types of long-range interactions. So they have to obey a certain condition. This condition is called the summability condition. We call it that because it means if you sum the interactions between any site and any single site and all the other sites, their absolute value is bounded by some constant that's independent of system size. So C naught is just some constant independent of system size. And so this condition, we need this condition to prove our theorem. And by the way, this condition is satisfied for any power law whose decays faster with a decay rate which is larger than the spatial dimension, which in this case is 1. So for 1 over r of alpha for alpha greater than 1, this would hold. And so what does our theorem say? Basically, it says if you obey the summability condition, then you basically have stability. So there exists some finite constant lambda naught, such that if your long-range interaction is weaker than that, then you have everything you want. You get a unique ground state with a finite energy gap in both sectors. And the splitting between the sectors, that's the splitting delta, is at most exponentially big in the system size. Okay, so everything works out in this case if you obey this condition here. And yeah, I'm not going to prove this theorem here, but just to give you a sense of how we prove it, it relies on perturbation. Basically, what we're able to show is that if your long-range interaction obeys this condition, we can prove that perturbation theory converges. Perturbation theory and lambda converges, and once we prove that perturbation theory and lambda converges, then we can show this exponential graph.
What is the Hamiltonian that corresponds to U of lambda?
You mean what generates that? So that's the generator of quasi-adiabatic evolution, and it's not quite the regular Hamiltonian. I could maybe describe it afterwards, but the key point is if your original Hamiltonian is local, the Hamiltonian that you get from this quasi-adiabatic continuation is also basically local. Yeah.
Can you repeat the condition on alpha or if space is d-dimensional?
So this theorem, yeah, I'm explaining in the one-dimensional case, which is why I said alpha greater than 1, but in d dimensions, this will be alpha greater than d.
I see.
Yeah.
Just to clarify, when you say H has a unique ground state, and modulo not displaying, right? It's supposed to
A unique ground state in each
only
sector.
in sector.
Yeah. So it has 2 ground states. Well, 2. They're not. They're 2 nearly degenerate ground states with a difference which is specific. Yeah. Any other questions? Okay. So as I said, yeah, we proved this using perturbation theory, and perturbation theory converges in this regime. And I should say, by the way, if the summability condition is violated, it's easy to show that perturbation theory won't converge. So it seems like it's hard to make this theorem any stronger.
Okay, can I ask that one?
Yeah.
And when it's not valid, okay, you would split the mini gap, but do you also close the gap?
So you can come up with examples, which maybe I can tell you about afterwards, where either of these can break down. Yeah, you can the gap can close. But they're a little bit, well, I'll talk about this. They're a little bit unphysical in the sense that for natural choices of sign, like the kind of, as I'll explain, like this lambda, if lambda is positive, those kinds of instabilities don't happen. But yeah, but this theorem applies for, it's a perturbation theory thing. So for perturbation theory to work, you need both signs of lambda to be well behaved, and that's where the problem comes. Yeah.
Should I interpret this lambda norm? Is this really a phase transition, or is this just where your perturbation theory?
That's just where perturbation theory breaks down. Yeah, we can't say anything. This is a general theorem. I mean, I explained it for this particular model, but it's actually a pretty general theorem for arbitrary two-body interactions. As long as each separate operator, like in this case sigma x, each separate operator commutes with the symmetry. So I explained it in this particular case, but it's a general theorem for any two-body interaction where the single body parts of the two-body interaction separately commute with the symmetry. And so yeah, this lambda na is just, that's where perturbation theory, we can no longer prove convergence after that.
But one could speculate that is
Oh, so for this particular model, yeah, you can ask what happens. That's a good question. I mean, I think probably for lambda sufficiently large, depends on the structure of F, you could certainly get phase transition. Yeah, this is general theorem for any X, but right, for many choices of F, you would get a phase transition. Yeah.
So you said that this is also true for arbitrary dimensions, except I guess the sum will be sum over all sides.
Yeah.
Okay. And alpha becomes alpha greater than D.
Yeah.
That's the only difference.
That's the only difference. Yeah. Yeah. So, okay, so I mean, this theorem is nice, but it's not fully satisfying because it don't, you know, for example, in the one-dimensional case, it only applies for alpha greater than 1, but in the d-dimensional case, it only applies for alpha greater than D. And many physical situations, we have power laws which are less than D. So most prominently in the quantum Hall system, we have a 1/r interaction in 2 dimensions. I mean, this theorem doesn't apply to quantum Hall for many reasons, but at the very most fundamental level, it's that this parameter regime is off. Like it's beyond the regime of stability, the 1/r interaction in 2 dimensions. So the next question we wanted to think about is, okay, it's great that we have this stability when alpha is greater than D, but what happens when alpha is less than D, or in particular, in this case, alpha is less than or equal to 1? And so I'm going to focus on the case, again, I'm going to focus on this very specific model for concreteness. I'm going to focus on the case where lambda is greater than 0. If lambda is less than 0, it's actually easy to show you get an instability at infinitesimal lambda. As long as once alpha is less than or equal to 1, at infinitesimal negative lambda, you get immediate instability. Okay. It's like a first order phase transition to like you know, basically like it's kind of easy to understand because let's see, should I go back to Hamiltonian? If lambda is negative, so I'm just let's see. Yeah, so this term here, what happens is this term here has become super extensive. When you're in the regime where alpha is less than or equal to 1, the norm of this term scales larger than L. Okay, so it tells you that this term can give you an energy contribution which vastly outweighs this, which is always of order L. So in particular, when lambda is negative, and let's say F is, you know, positive, it wants all the sigma x's to say equal 1 or something. So you get an immediate first order phase transition. Yeah. But that value of lambda, what I want to point out is, though you do get that instability, it's not one that would necessarily be of physical interest because, for example, in this setup here, that would correspond to like an attractive density-density interaction. Okay, so we're kind of interested in the repulsive lambda. Although perturbation theory breaks down, there's no, that doesn't mean that for positive lambda, the more relevant case, that there isn't something more we can say. So, okay, so that's what we're interested in, positive lambda where there's no instability, but in this regime. And so this turns out to be, it's not an easy question to answer, what happens in this regime, because perturbation theory, there's no hope of using perturbation theory, as I explained. What we did is we kind of found out some toy models, some slightly simplified models where we can make progress. So this is the toy model we considered. Instead, basically, we replaced the power law interaction with an all-to-all interaction that scales with the system size with L to the alpha. So this kind of corresponds to replacing, instead of 1/r to the alpha, we put 1/L to the alpha. L is fixed, it's the system size. And again, we're going to consider alpha less than 1. I'm going to consider alpha strictly less than 1 and lambda greater than 0. And so we want to understand for this model, how does the ground state splitting scale with L? And it turns out that for this model, this sort of toy model for long-range interactions, we can get an exact asymptotic result for the splitting, which I have written here. So this is the splitting, this is the log of the splitting. the log of the splitting scales like a power of L. It's not L to the first power, which would be exponential. It's L to the 1 plus alpha over 2. And this is some term which is smaller. So this is an asymptotic result in the sense that log delta divided by this goes to 1 in the limit L goes to infinity. And so just as an example, if alpha is 1/2, it would scale like you put in 1/2 here, you get 3/2 over 2, so 3/4. So it scales like e to the minus L to the 3/4. So you get a stretched, basically what we're finding for this model is stretched exponential. It's not power law. It's not a power law splitting, but it's also not an exponential splitting. It's stretched exponential. So this is our result, and I want to tell you a little bit how we derive this result. So how do we derive this result? So first, I'm going to take a detour. It's going to use kind of instanton methods. So I want to just remind you how you use instanton, how these methods are applied for a much simpler problem. And this is basically following the famous lectures of Coleman from, I guess, almost 50 years ago. So let's just think about a one-dimensional quantum mechanics problem of a particle in a double well potential. So we have just this Hamiltonian, and we want to know how does the ground state splitting behave in the semi-classical limit h bar goes to 0. And so of course you could do this with WKB approximation, but Coleman nicely explains how you can attack the problem using instantons. So how do you do it that way? So the idea, one way to rephrase this argument slightly is as follows. So this system has a symmetry, which in this case is a reflection symmetry, which maps x to minus x. And you can easily convince yourself that this splitting that you're interested in can be computed by this ratio of two traces, sort of a trace with an S operator and a trace without an S operator, in the limit where beta is large, but strictly speaking, not too large. But for very large beta, this will converge to the splitting delta. And so then our problem of getting delta is basically computing these two traces and taking their ratio. And so to do that, we use a path integral representation. So this becomes some imaginary time path integral. And then because we have this S here, we have this anti-periodic boundary conditions, x beta equals minus x naught, x is 0, and then this becomes periodic boundary conditions. And then, of course, since we're taking the limit h bar goes to 0, it's just controlled by the saddle points. So you have to find the saddle points of these two integrals with these boundary conditions. And so the denominator is really easy. It's obvious that the best case, you can minimize the action by just keeping x constant. So, and you want to put it at the minimum of the potential. So so let's say this would be the saddle point for the denominator, and then the saddle point for the numerator, it has to connect a point with x with minus x. And so the easiest way to get that's a little bit harder to get, but the easiest way to get that is solve the classical equations of motion. So you're looking for some mode, and because it's in Euclidean time, you're effectively working in a negative inverted potential. And so you want to find some classical motion that starts somewhere and then comes back to the opposite point. So it's this rolling motion where it starts at the maximum and goes to the bottom. So it's this so-called instanton path, which very rapidly tunnels from minus A to A. I think that's why it's called instanton. It happens kind of almost instantaneously, at least at some finite time. It tunnels from minus A to A. And so, so these are the two saddle points, and physically, this is somehow describing the process, the tunneling process. And then to get the splitting, okay, we put it back in our path integral is going to be approximated by e to the minus s evaluated at the two saddle points times some determinantal factors, which you can work out. Okay, and that's how you can get the splitting. Okay, so that's the classic way of handling this problem using instantons. And the reason I'm explaining this to you is because we can use the same approach in our system, as I'll explain in a second. Okay. Any questions? Okay. So let's go back to the spin model. So in the spin model, I've rewritten the model like this. So this is our sigma z interaction. This is the sum of sigma x, which I'm calling mx for kind of like magnetization. And so this is the model we're interested in, and we want to understand how the splitting scales in the limit L goes to infinity. So how do we? At first glance, this looks like it's totally unrelated to this, single particle quantum mechanics problem. But we can relate the two as follows. So the first thing we can do is we can use the same argument as before to say, okay, the splitting can be computed by this ratio of these two traces with the S and without S. In this case, S is the symmetry product of sigma X. Okay, and so then we can write out what is our Hamiltonian. It's this H naught plus lambda mx squared. So we have to calculate these two traces. And now what we're going to do is we're going to trotterize this exponential. We'll basically break it up into pieces. And so we'll write it as e to the minus beta over m to the mth power. Okay, the same thing for the denominator. I guess I don't even have to say limit m goes to infinity here. It's an exact expression for any m. But anyway, I've written it that way. And now, once we've written it this way, then the last thing we do is, we look at this. This is kind of a hard term to handle, this mx squared term. So we can decouple that with the Hubbard-Stratovich identity. So we have this mx squared. We can write it as this is an operator identity, to be clear. So we can write this operator here as e to the I mx phi times some phi squared, where phi is some parameter we just integrate over. And then using this operator identity, we can substitute that in. So we can think of this as a product of m terms. In each term, we substitute this in. So we get m one-dimensional integrals over m different fields, say phi 1, phi 2, up to phi m. And so it's easy to see once you do that, you're going to get an m-dimensional integral over phi 1 through phi m. So it turns into a path integral. And the path integral looks like this. So this term here comes from the Hubbard-Stratovich coupling. And then this SA at phi, this just includes the H naught term, which is coming from here. And this IMX phi is coming from here. Okay, so at the end of the day, we get this path integral. And now we've reduced the problem to kind of what looks more like a 1D path integral. Phi is just some real valued single dimensional field. But at the cost of our action being rather complicated. Okay.
You're using the fact that the total magnetization commutes with H naught? Because you're using CPH.
Let's see. Where let's see. Am I using
You're using the product of exponentials and the sum of the exponential of the sum.
Let's see. Did I do that? Oh, maybe oh no, sorry, I did. I guess I did. Which step are you referring to? This one. So here, actually, now that I think about it, I said this was exact. I misspoke. I forgot. No, I do need this, right? Because I trotterized it, right? Yeah, I'm just using trotterization, right? I can always write the exponential because m is going to infinity. I can the error term that I get when I do this. Yeah, sorry. Yeah, I said exact. I wasn't thinking. It's not exact. So it's only in the limit m goes to infinity. That's correct. Is there other question? Or okay. Okay. So now we've reduced it to a 1D problem, and then we do one last thing. We make a change of variables from phi to theta, and then what was originally like a phi squared becomes theta dot squared. And what was originally a phi becomes theta dot. And now this thing is really starting to look like a 1D particle. It's like the kinetic energy term theta dot squared. And this is like some still complicated function, but it turns out to be reduced to kind of a potential energy in a certain limit. So it starts to look like a regular path integral. The last thing I've done here is the S, which is the symmetry. This is very important, can be written as the exponential of this magnetization, e to the I pi mx. And so, okay, so this so far is an exact expression. And now, how do we proceed from here? Well, the key point is that we expect that these two actions here, although they're rather complicated, we expect them to be extensive to scale with L because they're kind of involving traces of an extensive system, right, of size L. So we expect these to scale like L, and this scales like L to the alpha. So kind of every term in this exponent is very large as L goes to infinity. So we can use the saddle point approximation. And interestingly here, the limit L goes to infinity plays the same role as H bar goes to 0. So fluctuations are suppressed in the thermodynamic limit. So that's what's nice about this. It naturally suppresses fluctuations as L goes to infinity. And then yeah, there's a step or two I'm skipping here, but these actions, although they're hard to evaluate for a generic path, you can kind of find the optimum path with some approximations. And what you find is for the denominator, the path, that's easy again. It's easy to show the denominator. You can prove rigorously it's maximized by straight path. The numerator takes a little more work, but it turns out to be a tunneling path. The reason it goes to pi has to do with this pi here because, well, maybe that's a little hard to explain, but basically you want the integral of theta, you kind of want this term to cancel this term. So you need the integral of theta dot to be equal to pi to cancel this. And so that's why the max that it turns out that it has to go from 0 to pi. And so again, you follow the same rules. You can calculate the action of these two paths. And what you find is that this instanton is even more instantaneous than in the Coleman case. It actually, the time scale for the tunneling goes to 0 as L goes to infinity. And that's the reason why you get this stretched exponential behavior, because the time scale goes to 0, but you have to multiply by L. So you get this L to the 1 plus alpha over 2. And so this is where the stretched exponential comes from. It's basically because, on some level, it's because there's this, I guess, what is the statement here? Yeah, okay, maybe I won't go into that. But yeah, the tunneling becomes very rapid. Yeah.
I'm just wondering, what's the theta is field?
What does it mean physically?
Yeah, what's the meaning?
Very good question. Yeah, I had a slide that I deleted, but I can still explain it. So theta, you can see what theta is from. You can get a hint for what theta means here because you have a term that goes like mx times theta dot. So this is like a very phase term. So typically that means that you should think of theta as the variable that's canonically conjugate to mx. And so mx is like the spin in the x direction. So theta is the angle in the yz plane. So what this is describing is there's some really big spin, we could call it m, that's initially pointing at theta equals 0. So that's like, so theta is the angle in the yz plane. So this is the x-axis, this is the yz plane. So it's originally pointing at 0, and then it tunnels to pi. So it goes like that. So the spin is pointing from all up to all down. Yeah. Okay, so fine. So we got the stretch exponential. The last thing I wanted to talk about is I said, that I was going to tell you a little bit about 2 dimensions. So let me tell you about a model in 2 dimensions. And it turns out that this method of solving the 1D case just immediately applies in this case. So what's the model in 2 dimensions that I want to think about? It's the Tor code model, which I guess has been discussed in several lectures. It's the exactly solvable spin model where the spins live on the links of the square lattice. It has 2 types of terms: a star term, which is a product of 4 sigma x's, and a plaquette term, which is a product of 4 sigma z's. And so this is an exactly solvable model that is known to have a topological ground state degeneracy when you put on a torus. It has 4 degenerate states. And then I want to add on this long-range interaction, sigma x with some f. And as I said before, when lambda is 0, this has an exact ground state degeneracy. But when I turn on lambda, we expect this degeneracy to split, and we want to know how does the splitting scale with the system size. And this model, I want to just mention again, there's a motivation for it. Like, why did you might ask yourself, why do you use this particular kind of coupling, sigma x? Why not something else? So there's a reason for that, because ultimately, I think what I'm interested in studying is fractional quantum Hall systems. But this model that I just wrote down can be mapped exactly onto another 2-dimensional model, which I won't describe. It's discussed in this paper. There's another 2-dimensional model you can write down that's exactly equivalent to one that I wrote. And this other 2D model has U1 charge conservation. It has fractionally charged excitations. And that density and that interaction I wrote down, it looked a little arbitrary, sigma x, actually is a long-range density interaction. So the point of view that I take is that this other model is kind of the closest we can get to a quantum Hall system. It has many of the features: fractional charge, topological order, long-range density interactions. And so we would like to study this other model, what happens to the long-range, what happens with, say, Coulomb interactions. And that question exactly maps onto the Tor code problem. So that's where this model is coming from. It's basically an alternative way of writing this other 2D model, which is very similar to quantum Hall systems. So that's the motivation. Yeah.
How you want?
So it's in the other model, which the other model has extra degrees of freedom that live on the sites. And I could explain it to you. I didn't think I had time, but it has a cluster charge term and it has a ring exchange. It's like a Bose-Hubbard model on this decorated square lattice where you have sites at the on the site. You have bosons living on the sites and on the links. It's like a Bose-Hubbard model. It has a U1 charge conservation, and it has a ring exchange term. And you can exactly map its low energy manifold of states onto this Tor code model.
But this model doesn't.
This does not, that's right. But if you wrote it in the other variables, you would see the U1 charge conservation, and you would see that this actually is a density. It's a little, yeah. So that's the kind of motivation. So again, we can ask what happens to the splitting. And I just want to tell you the results in this case, and I'll wrap up. So there's two cases we can think about where we can kind of have results. So one is the case where this long-range interactional base, this summability condition. So the sum of all the interactions is smaller than some constant C naught. So for example, that would apply to the case where the interaction is like 1 over r to the alpha for alpha greater than 2. And so in that case, the stability theorem I wrote down, we didn't do this in our original paper, but I'm fairly confident we can generalize that theorem to apply to this model. And so assuming that's the case, it would give a splitting that's exponential, quite generally exponential. Basically, we could prove perturbation theory converges in this regime, and we can get this exponential. So if the power law is greater than 2, I think we just can prove exponential. If the power law is less than 2, then again, we have very few tools, but we can treat this kind of toy version of long-range interactions, this 1 over L to the alpha. It turns out we can only treat that for alpha less than 1, just like we did in the 1D case. And actually, you can go through exactly the same kind of calculation we did, exactly this Hubbard-Stratanovich approach to solve this problem. And you find exactly the same kind of splitting. It's, again, this stretched exponential, 1 plus alpha over 2. So actually, the Tor code model with alpha less than 1 is very, very similar to this 1D model. That's part of motivation. Yeah.
We kept it between 1 and 2, but if I take alpha going to 1, you also get exponential, right? So it's probably that alpha between 1 and 2
could
is
be.
also exponential.
Yeah, it could be. Yeah, that's well, I was going to say on the next slide. Yeah, we don't know what happens there. We don't have anything that can really deal with that case, but we can make a guess, right? So, okay, so then I just wanted to summarize then the results that we have. So in the 1D case, for alpha greater than 1, we have this theorem, which says it's exponential. For alpha less than 1, we don't really have, we can only treat this all-to-all interaction where we get this behavior, but we believe that this applies for regular power law. We have some other evidence for that, which some other models we can solve. But so this is kind of a conjecture. And then alpha equals 1, we don't really know what happens. Maybe it looks like this, but it may have some logarithmic corrections. We're not sure. So this is actually, unfortunately, the case that's, well, it's unclear if this is the most visible interest, but this seems to be of some interest. The 1 over r, we don't know what happens exactly. Then in 2D, again, for alpha greater than 2, it's exponential. For alpha less than 1, we can't say for sure, but we have the all-to-all model, we can get this stretched exponential. And then between 1 and 2, as Claudia was pointing out, we don't really know, but you might expect it will be exponential, maybe with some logarithmic, that have some corrections. But yeah, so that's what we know. So I'd say the punchline of this is, so far, it looks like these long-range interactions aren't too problematic to, let's say, if I had to guess, for quantum Hall states. They may change the splitting from exponential to, give some logarithmic corrections or something, but it seems unlikely that they're going to give destroy it completely. So yeah, that's all I was going to say. Thanks for your attention.
So in your 1D case, what goes wrong in the instance calculation if alpha is greater than 1?
Yeah, what goes wrong is that the splitting, so that, it's this thing. So delta tau scales like L to the alpha minus 1. And so this is actually the only reason we can evaluate the action at all. Basically, for paths that tunnel very, very rapidly, we can evaluate this, what looks like this very complicated time-ordered exponential, because it happens so quickly. We can use some approximations. But if as soon as alpha becomes even 1, certainly greater than 1, the tunneling time isn't short anymore, and then we can't evaluate these actions. So I mean, this is still exact. So we can't go
The
further.
time is no longer localized.
Yeah.
I see. Thank you.
So I got a little bit confused. You're writing f of r as 1 over L to the alpha.
Yeah.
So what is the connection? How do I think about it as long range interaction?
So it's long range in the sense that if you look at two spins that are separated of order the size of the system, they have similar interactions in this all-to-all case. So it's scaled so that a typical choice of two spins will have an interaction similar to that of a power law. But the short range piece, the piece where you have spins that are, significantly closer than the length of the system, this is a weaker interaction. Yeah. So yeah, so it's the closest you can get to a power law interaction if you try to do all-to-all.
For 2D topological orders,
Yeah.
can we adopt the argument that say those anion data are still well defined?
Right. Yeah, we haven't thought about that. You mean like whether, like can you do braiding or something?
Yeah.
Yeah, it's a good question. Yeah, we haven't, we don't have anything sharp to say about that, but certainly it's a good sign if, well, again, we don't know for sure, but if the splitting is this small, like stretched exponential or exponential, then it seems like likely a lot of those notions will survive.
Can you say something about the value of the exponents?
Which ones?
And the ones for your simple model, which can be simulated numerically.
The values of the exponents. So which one you're referring
So
to?
when you theorem and any of the exponents.
Any of these? Can they be seen numerically? Is that the question?
That's a question.
Um,
You actually see when you practice, you can see the difference between. So
Ah.
that's your polynomial.
Right. Yeah. So, yeah, we haven't tried to do really serious numerics. We did a little experiments. It's actually not so easy. It's not so easy to distinguish these kinds of behaviors especially if you can only go to fairly small system sizes. But we did do some very simple numerics on that 1D model, and it did look. So we did the 1D model with all-to-all interactions, where we have more or less an exact analytic result, and they did seem consistent with our analytic results. So we did see this, but I'm not sure it's rock solid numerics because we could only go up to, I don't know, like 10 spins or something. Very few. We probably could do more, but maybe 15. But it's all-to-all interactions, and we were just doing exact diagonalization, nothing fancy.
Even then the exponential is like e to the -10, which is like less on a, to really measure,
Mhm.
if you're measuring those gaps, it could be really
Yeah.
fast.
Have you ever looked at entanglement structure if Leon Haldane holds in the presence of these terms?
If Lee and Haldane holds,
Leon Haldane's conjecture.
you mean about like the properties of the
Yeah, the low energy
Entanglement spectrum?
entanglement spectrum equals some. If you don't make it too large.
No, yeah, we haven't thought about that. Yeah, I don't know. That's
In the case when you have real power law behavior, is the problem still reduces to finding a certain instant solution? Or
you mean if we tried to do this case
yeah,
with
this
the true?
case,
Well, so the problem in that case, so we could still do everything we did up to, let's see. The problem is we don't have something to control fluctuations. So let's see, or maybe I can go up to here or something. I guess I can go a little beyond this. Yeah, so we can still write this down. This is all exact, but we no longer have this parameter L. So what we'd have to do is we'd have to introduce a theta parameter for each spin. And so then we don't have this overall factor of L. We have a D. We don't have a single field we're integrating over. We're integrating over L fields. So we have nothing to control the fluctuations. Like, we don't have L no longer controls the fluctuations
on
because
the other hand, the action is still, if that exists, the action is still large, right? It's instantly if it exists.
yeah. So I think we
We
could do so if you just naively do that, you would get the same scaling. But I think we weren't confident that it was well controlled. Now, the one thing we could do, which is kind of along the lines of what you said, is the other piece of evidence we have for the power law is we wrote down another model, which is like a quantum rotor model. It's not a spin model. And then there we can do a semi-classical expansion. We can send H bar to 0. So we did exactly this. But we can send H bar. We now have a parameter that controls it. And so then we can get an exact asymptotic expression H bar. And again, we see the same scaling. But that's also not fully controlled because there's some kind of order of limits issue. Like we're kind of taking the limit H bar goes to 0 first. And yeah. But it seems likely. That's why I said it's conjecture that it scales this way.
Other questions? That was Michael again.